team upstairs were not enough to finish the entire wall. To get the job done, Engineer Daniel and other workers of the house built a pulley to lift the bags of cement quickly and easily, rather than by carrying it upstairs. Using the hanging end of the crane, the workers attached a 40 kilograms of bag of cement and tied it down. Engineer Daniel, who weighs um, 75 kilograms, is standing on a horizontal surface with a coefficient of kinetic friction of 0.020 and pulls the other end of the rope with the force of 425 newtons to lift the hanging bag of cement and reach his position. What is the acceleration of the system and what is the tension of the rope? So, um, I will give you the illustration above. We'll be utilizing GIF to show the illustration, but I can also draw it for you to analyze in and understand it properly. So it was said that Engineer Daniel is building a house. Sorry for the drawing. I'm not really good at it. So it will be there's four parts. So let's assume this is the last one. So one, two, three. One, two, three, four. So here is the floor. So Engineer Dane is at the above, um, pulling um, a pulley. So at the end of this, there's the cement. Then there's a given value for its mass. So let's try first to write the um, given values. So the given values are first the mass sub one. Let's set that mass sub one is the hanging object. So wait for a while. So let this be the mass sub one or the hanging object. Then engineer drain is the mass sub two. So mass sub one or the hanging object weighs 40 kilograms. Then the next one is Daniel, the mass sub two, wherein he weighs 75 kilograms. So then you should take note that Daniel is pulling the rope wherein the hanging object is present. So he's pulling the hanging object going here with a 425 newton supplied, force applied. So let's write it down. 425 newtons. 425 newtons or 425 kilograms meter per second squared. The next given is um, there's the kinetic friction. The kinetic friction is um, 0.020. So let's take note of that to illustrate it properly. So if the kinetic friction, we all know that the kinetic friction is the opposing force. So if this is if thing is going here, therefore the kinetic friction is going opposite the direction of the applied force. So meaning the kinetic friction is going here. Wait. Let's try. Yeah. So the kinetic friction is going here. There. So next given is I think that's all. But also we should always consider that um there's a given quantity that is always constant, which is the value of gravity. Gravity which is 9.81 m squared. Oh, so I think we all have it. So let's try to illustrate properly the illustration. So to determine the to determine the exerted forces or external forces. So in here, in the hanging object, there's the tension force exerted by the rope. Let's take note of that. Then there's the weight. Then also in the on engineer Daniel, there are different external forces, including the force applied, the kinetic friction, and also the weight force due to gravity and the normal force, which is exerted by the surface to engineer Daniel. So I think that's that. So for the next part of the CRESA, the required to find. So it is asked that we should find the acceleration of the system and also the tension on the rope. So again, here is the tension force that we're looking for and the acceleration by the system. It means the acceleration of Engineer Daniel and acceleration of the hanging object while going up. It's the same. So let's try to proceed with the equation. Let's try to derive some equations. So what we're looking for is, or what we're involving are Newton's law of motion, or I think it's the second law of motion, wherein the equation is the summation of, wait for a while, summation of F equals, um, no, no, MA, meaning force is equivalent to mass times acceleration. But in this case, we're looking for the acceleration. So let's try to derive the formula. So if we're going to derive it, we will set acceleration or the required to find, then transpose mass into the left side or to the right side. So it will become the summation of F over, oh wait, I'm sorry for the delay. So it will be summation of F. No, let's try to determine all the summation of forces exerting or happening in the system. So in the summation of force, we can see that um um there's the applied force. The applied force is this one. So let's try to put it here of A. Then the opposing force, which is the kinetic friction here, this one. And it is opposing the applied force, therefore it is negative. So we should take note of that one, especially it is the kinetic force. Then lastly, the hanging object. So the hanging object also exert a force opposing the system, which is its weight. So since we're involving horizontal surface, we're going to just write the weight force equivalent to the mass times gravity, or the mass of the object one, or mass sub one times gravity. So that's it. That is the summation of forces exerting in the system. So next part is we're going to take note that in this part, there's two masses involved. So we should take note that if we're going to determine the acceleration of the system, meaning the system as a whole, involving including the mass sub 1 and mass sub 2, the masses should be also summation of mass here. Let me change this one. Should be like this. Sum of masses. So now let's try to put this equation in find the acceleration. So it will be like this. Acceleration is equivalent to um, F sub A while F sub A oh, minus f sub k. Oh, I think f sub k. F sub k. F sub k. Then so f sub a minus f sub k minus m sub 1g all over the summation of masses, which is the m sub 1 plus two. So we forgot to I forgot to show the formula for computing the kinetic friction. I'm sorry. So it will be like this. Kinetic friction will be um mu k times m or the mass of of the object wherein the first friction exerted. So meaning we're going to utilize the mass of engineer Daniel. So it will be like this. Mass sub 2 times the gravity. Right. So this one is the weight of the hanging object. So let's try to replace this kinetic friction with this formula with this one. Let's try to replace it. It'll be like this. So there we got the first equation, the equation for computing the acceleration of the whole system. Then for the next equation, we're going to try to find the tension exerted on the rope. So for the tension on the rope, we're going to look for the summation of um, F in the y-axis. Since we're just involving the tension, which is acting in y-axis. That's why summation forces in y-axis on the hanging object. So it was we all know that for computing the tension force, there's the um, tension minus um, the weight of the object, weight of the object. So therefore, we're going to utilize the mass sub one. Then if we're going, we all know that the um, force, this one, I mean this one, that force is equivalent to mass times acceleration. So let's try to put mass times acceleration. Mass times acceleration equals T minus, let's just copy this one, mg. But in this part, we're going to look for the tension force. So let's try to derive this formula into a variable where we can find tension. So it will be like this. Tension is equal to mass, the mass of the hanging object, mass sub 1, times the acceleration of the system minus um, sub 1 times the gravity. So there, we have two different equations. Let me are two different formula for finding the acceleration, this one and also this one. So let's proceed with the solution part. Um, Here, if we're going to solve, let's copy the formula here. Let me copy this one so you can follow me. So let's try to substitute all the given we have in this formula. So we have we We have 425 newtons, also which can be derived as 425 kilograms meter per second squared. Then minus um, mu k, which is the coefficient of kinetic friction, which is 0.020 times the mass sub 2, which is the mass of Engineer Daniel, 75 kilograms, and the gravity, which is 9.81 m squared. There. Then next, the weight of the hanging object, which is um, 40 kilograms times 9.81 meters per second squared. All over the summation of masses, which involves 40 kilograms, the mass of the hanging object, then the weight of Mr. Daniel or Engineer Daniel. So that's that. So let's try um, to solve this one. So if we're going to put in a calculator, we're going to have um, 0.155. Then if we're going to round it up to the nearest two decimal points, we're going to have um, 0.16. And to know what unit we're going to use, let's try to cancel units. So for the cancellation of units, since if we have here kilograms meter per second squared, we're going to add and subtract in other variables. The only time we're going to cancel units is when we're dividing or multiplying. So in this case, we're going to cancel the kilograms. Since you have these kilograms, then it will be canceled here. So we're going to have what's left is um, meters over per second squared. So let's try that there. So our acceleration for the entire system is, let's try to change the color, think blue. So the answer for the first question is 0.16 meter per second squared. So we have one answer. So let's proceed for the second part. Going to look for the tension force. So in this case, what we're looking for is the tension force exerted on the rope. So let's try to copy the formula. If we're going to solve this one, let's substitute the values. So for the mass sub one, we have 40 kilograms times the acceleration, which we got a while ago, 0.16 m square of m per second squared. Then 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 subtracted from the mass of the hanging object times the gravity. So you can put this one in the calculator and you're going to get 398.8 newtons, or let's first put um, the units that we have. So kilograms times meter per second squared. So we're going to have that, or also known as 398.8 newtons, wherein the new unit we're using for force. So we have the solution now. So as you can see, you've already answered the required to find. We have the acceleration of the system here in this one. Wait for wait, I moved. and the tension force is exerted by the rope on the hanging object. So I think we can write the answer, the final answer. So the question is, um, what is the acceleration of the system? So the acceleration of the system is 0.16 meter per second squared. It is based from the given quantities wherein there are two objects involving the 40 kilogram hanging object and the 75 kilograms body that is exerting 425 newtons. And also there's the presence of 0.020 kinetic friction. So we have, for the total acceleration of the system, we have 0.16 meter per second squared. And lastly, the tension force that is required to find the value that we're looking for is 398.8 newtons, or 398.8 kilograms meter per second squared. So I think that's all. So I hope you learned something from this. So thank you for watching.